So now in this video, we're going to look at the NPN bipolar junction transistor in more detail than I usually look at it. So a lot of times you'll see BJT for the abbreviation for bipolar junction transistor. The NPN is the chemical makeup of the transistor, the NPN bipolar junction transistor. And so here we have it, and I also wrote the polarities. So there's a couple currents. That's the first thing you want to keep in mind that we deal with. We have base to emitter current, and then we have collector to emitter current. And sometimes there's no current flowing at all. And then if there's current flowing from base to emitter, there's probably current going collector to emitter. But there's only collector to emitter current if there's base to emitter current. So first, let's talk about the base to emitter current. If you know how to power a diode, you know how to power the base to emitter. So it is a forward bias diode. So when you learn about diodes, you learn about p-type material and n-type material. P-type material you call the anode, and n-type material you call the cathode for a diode. And when the anode is more positive, the cathode more negative, a voltage difference of about 0.6 volts or so, current will start conducting. And so you got to limit that current, usually with a resistor. And so you're going to drop about 0.6 volts from the resistor, and if you have a 5 volts, that'll leave about 4.4 approximately across the resistor. 10 kilo ohm resistor, you'll end up with about 0.44 milliamps. So that is one thing. You just have, generally speaking, low amounts of current going from base to emitter. So now let's talk about the collector. The collector, when it comes to the base, is usually a reverse bias diode. So you can see p-type material here towards negative, and because we can go all the way to as low of a voltage as we have at the emitter, and then the n-type material more positive right there when it comes to the collector. So this does work pretty good as a reverse bias diode. You can build up, I don't know if it's 30 volts or whatnot. If you go above 20 volts, I would definitely check the data sheet for the 2N3904, but you can get a pretty high voltage across there when the collector is more positive than the base. The emitter, if you accidentally wire that to be more positive than the base, somewhere about 6 volts it'll start conducting. That's very bad. It does not work as a rectifier diode. It only works good for a forward bias diode, whereas the collector of the base does work good for a rectifier diode. So that is the main thing to understand right there. So now we'll do those diode tests. I am not powering the circuit right now, and the meter is going to provide the power. So we got the middle pin, the orange jumper. Since this is a 2N3904, I know that the emitter is down there, the base in the middle, and the collector on top. But if you're not sure, you can just set a meter to measure diodes. So right now it is continuity right there, and I just leave the red probe in one spot except for high current for this meter. Some meters you may have to move it, but it beeps if you have a direct connection. So if I just measured across the wire or something, I would know it's not a short circuit. It would beep. So I hit the button again. Now we have the little diode schematic symbol. So I know that the middle jumper is to the base, and then the emitter is down here. But as I said before, it's a forward diode, somewhere around 0.6 volts, and then at higher currents it'll be 0.7 volts right there. So it'll be somewhere between that range. And a collector, same thing right there. So that's how you can find the base. If you get, with the black probe here, a low voltage reading of about 0.7 volts on each side. Where the red probe is will be the base. So if we got the black probe to the base, we will not get any reading when we go to those two. That's because they both need more voltage than the meter is applying to test it. And now I have the power applied, the power supply at 5 volts. It's not providing any current now. I move the transistor up and connect the resistor to the base. So let's do a quick, right there, resistance. You can see the ohm symbol. This is an auto ranging meter. The vast majority of things, it just auto ranges. You just have to tell it what you want to measure. It does the rest. So the transistor does not go to any side of the power supply. So the resistor is not being powered. We can measure the resistance right now, and it's just shy of 10K right there, 10,000. So that's kilo ohms up in the top right symbol. Now we can measure the current, and this is where you have to be the most careful. So it'll be below the milliamp range. So let's go to milliamps. If we thought it'd be low microamps, we could go to microamps right away. But it's a good idea to start with milliamps if you think you might hit the milliamps. So now we're going to go to the emitter. We have to complete the current path. And I'm pretty sure you could probably see that, but just in case, you can see we got the current that I estimated, the 0.44 milliamps. If you need more precision, you can go to microamp and measure that right there. So it's just a diode circuit, pretty straightforward. We covered that. So now we're going to move on. And so now we're back to the diagram. I did turn the multimeter off. It has a dial that goes to off, and if you don't have a off diode, just an off button, get it off of measuring current. That's the most dangerous thing you can measure by accident, too much current. But in any case, we looked at the base 2 emitter. Basically, it's like a diode, and you control how much current flows through it, usually with the resistor. There's some other ways too. But the main thing is, you got the base to emitter current. You also have the collector to emitter current. So the general rule, the transistor will be cut off. It'll be off. There'll be no current to emitter, collector to emitter current, if there's no base to emitter current. So you need some base to emitter current for there to be collector to emitter current. And so if it's not conducting completely, it's still limiting current. That's called the active region. And when it's conducting as good as the transistor can for any given circuit, that is called saturation. So the main rule though is for each charge going through base to emitter, the transistor is going to want to let through a large multiple amount of current. That's why it's called an amplifier. A small current is controlling a larger current in the vast majority of transistor circuits. So I already wrote here, no base to emitter current ends up being no collector to emitter current. It's kind of small. I'll zoom in a little bit right there. It has a gain. So unfortunately, the gain is not very stable, and so you'll have a range of gains under different circumstances for a particular transistor. And I think for the 2N3904, which has a maximum collector current of 200 milliamps, according to the data sheet I read. Always verify information with the data sheet. And there's the pin layout: left pin emitter, middle pin base, right pin collector. But in any case, I think that one, the 2N3904, is mostly near a 300 gain. But you don't really have to depend on that too much. Mostly, you just have to look at the worst case scenario. Maybe at sometimes it will only have 100 gain under particular circumstances. So you make sure that you use a low enough value resistor here, where you'll have enough current where 100 times that will be the current. You have to put a load. That's the main thing, through a load. So if it has a gain of 100, that means you'll have 100 milliamps of collector to emitter current for every milliamp of base to emitter. And if it has a gain of 200, once you hit that 1 milliamp of current, 200 gain, then you can expect up to 200 milliamps of current from collector to emitter. The load, what you're powering, will probably lower that current by quite a bit, but that's the potential you have if you put 1 milliamp through base to emitter. So it doesn't have to have any collector to emitter current when there's base to emitter if there's enough resistance. Like when I measured the current from base to emitter, the collector wasn't connected to anything, no current was flowing through. I was only measuring the current from base to emitter. And then if you have a 300 gain, that could be a problem. We're not supposed to put more than 200 milliamps in current here. So you would make sure the base current stays low enough where you probably won't get that gain. But again, you should, because if it's 0.5 milliamps at 300 gain, that'll be 150 milliamps below the 200 milliamp limit of this one. But usually you have a load that is keeping it even well below 150 milliamps. But that's just something to be aware of, to understand the component a little more. So we have a small base to emitter current, allows many multiples. So now I wrote the 4 I think these are kind of the 4 most basic circuits. And then when you learn more complex circuits, they kind of add elements of each of these as you learn more complex ones. But in case you got the switch, so you just purposely apply, you have a fixed resistor and then a switch that either puts current from base to emitter or doesn't, but either way it makes the transistor saturate. Collector emitter conducts as well as it can, and the load will limit current from there. And then you have a current source, you set a voltage at the emitter, and from the voltage and the resistance across it, I should say, a certain amount of current will flow, even as the load varies up there. And then you have the emitter follower. The load is on the emitter side, and so the voltage you set at the base gets transferred to the load. And then you have the inverter. It's a digital inverter, not gate, where when the transistor is on, the load will be over there going to ground. It'll be off. When the transistor is off, then power can go through the load will be on. So they'll make more sense when you study those circuits in more detail, but hopefully this still helped you understand the NPN bipolar junction transistor better. And that's it. I will see you in the next video. Check out one of the other videos I'm posting. Click like, subscribe, the bell, all that. Donate to Patreon if you can. That helps out the most. I have links down in the description. But just watching many videos that can helps out a ton. Thanks to everybody that does that. I will see you in the next video.